Hi there, welcome back. Petrophysics rocks. Did you miss me? No upload last week. I took the opportunity to disappear off to the desert, out for a bit of desert sun in Dubai. It's quite cold here in Aberdeen in January and February, so thought I'd grab a little bit of a sunshine break. But I have got for you guys something great. This is the last video that I'm going to rescue from my website. It's a saturation height, a practical approach. Really the clarity of the Dutch mind. A guy called Jan Gehl, ex-Shell, put the original spreadsheet together and gave me permission to use it. As you see, I originally put this presentation out in 2011, so it's been out there for a while. I know a number of people have been able to use it, and where it's really helpful, obviously we've all struggled with other people's spreadsheets and cobbled things together, but this one is really hopefully quite nice and easy to follow. You'll have these videos as a reference to a how-to guide. It'll talk you through the Excel spreadsheet, what to put in what column, how to sort it. There are a number of charts that are all predefined and set up. It is still a spreadsheet, so therefore there is a little bit of effort required. But in my own way, I kind of think that the way that I've left this spreadsheet is actually good therapy for processing the data. Jan's latest spreadsheets were a bit more sophisticated. He included macros to do a lot of this stuff automatically. But I always like to keep it more manual so that you can commune with the data as you're going through this process. You keep an eye out for strange squirrely things like 100% porosities and negative water saturations and things like that. And as you go through this, you're getting more and more of a feel for your data set. As I say, these are originally 3 separate presentations, which through the magic of modern video editing, I've been able to sort of combine into one presentation here. Now, if you would like to have a copy of this spreadsheet, then contact me at the email down below. And whilst you're there, you could give me a like and subscribe and do all the good things that would help drive the algorithms. We're getting close to 100,000 subscribers. Oh no, sorry. We're getting close to a couple of hundred subscribers now, which is good, which is fine. It would be really appreciated, any interaction you've got. If you would like to have a copy of this spreadsheet, as I say, just give us an email down below, make a comment as well, what you think, interact with this a little bit. And if you find it useful, then perhaps you'd consider donating to the Aberdeen Royal Infirmary, Archie Children's Hospital. Whatever you can afford would be appreciated. As I say, this has been around for a while. It's been raising money for Archie from my other website, so it would be nice to start kicking things off with a bit of YouTube love, as it were. So hopefully you enjoy it. Saturation at height, a practical approach, an Excel toolkit. Okay, good luck with it. Let me know if you want a copy. Cheers. Thanks a lot.
This presentation is called Saturation Height, a Practical Approach. I've given this presentation to both the Aberdeen Formation Evaluation Society and the London Petrophysical Society, but the original spreadsheet from which it's based was given to me by my former colleague Jan Gehl at Shell, and he's kindly agreed that I can share this Excel engine with you. The idea is that hopefully we'll be able to provide you with a practical tool which you can use to tackle your own saturation height modelling problems. Obviously, we've all struggled with other people's spreadsheets in the past, and if we haven't written them ourselves, sometimes they can be a little bit tricky to navigate. But hopefully you'll find that the clarity of the Dutch mind has come to our rescue and provided us with a fairly clear spreadsheet, which I'll take you through, and hopefully you'll find it usable. If you email me, I will happily send you a copy of the spreadsheet that we're going to discuss here. Okay, so in overview, what I'm going to mention, briefly touch on a few common saturation height functions that you'll see about the place. Then we'll specifically concentrate on the lambda function, and this presentation is an Excel-based implementation of the lambda function. And I'll show you the example dataset and some workflows and the ins and out of the spreadsheet, so that when you come to use it, you'll know exactly what you have to do. So we'll go into a little bit more detail in the Excel workings of things than you might normally expect in a standard presentation, but hopefully you can use this as an aide-memoire if you ever come to use the spreadsheet in anger yourself. Then I'll show you some of the QC tools, and we'll investigate a few anomalies and some charts and cross plots in the tool that I've put in, and then we'll discuss briefly some complications, some diagenesis, fasces, and other geological nonsense that sometimes comes in to confuse our beautiful cross plot world. Okay, and then of course the presentation in Excel spreadsheets was provided to the delegates at the seminars. So if you email me, I'll happily give you a copy of the Excel spreadsheet as well. So here are a list of common saturation height functions. I've borrowed this slide from my cap pressure to flow rate presentation, and we'll be primarily interested today in the lambda function. The lambda function is a nice stable function that gives you good mathematical solution under most regression analyses, so it gives you nice stable answers and the regressions work out quite nicely. The nice thing about the lambda function is that it handles both long or short transition zones. So in this first example, you can see that it's a low relief structure and the oil saturation is primarily within the transition zone. It never really gets to a good irreducible water saturation, and you can see that the lambda function mathematically can cope quite well with this long, lazy transition zone. Also, in this example here, you can see that it can cope reasonably well with short and sharp transition zones, where the rock quality is good. As soon as you get above the free water level, the rock desaturates, lets a lot of oil in, and it suddenly turns quite quickly through here. In fact, I have got examples where it actually virtually turns through right angles. So the point I'm trying to make here is that the lambda function copes with both long or short transition zones. One area of weakness probably is that you can't tend to mix the two, so it doesn't cope. You can't change the curvature with the having long transition zones for poor rock and short transition zones for good rock. A function that is good for that is the Tamir function, which we're not really going to go into much detail about today, but I just thought I'd show you this 40s example. Here you can see the Tamir function, and what you can see is here at the 33 PU curve, the good rock, there's quite a sharp transition zone. The rock desaturates nicely and turns quite quickly, and here at the 13 PU curve, it's a bit more longer, lazier transition zone as the oil struggles to get into the poorer quality rock. And you can see that the Tamir function within one equation can cope with a range of curvature. So you've got a varying degree of curvature with rock quality, which is a nice feature, and it often stops a lot of arguments when you present this kind of stuff to reservoir engineers, because intuitively it looks more like a set of core capillary pressure curves that they're used to expecting to see. It's a difficult function, or this implementation of the Tamir function is a little bit difficult in the regression analysis. You have to do the regression in two parts, and sometimes the porosity terms conflict with each other and can crash the equation. So it's a bit of a tricky one to get a stable regression result for. So therefore I'm not going to present how to do the Tamir function because I don't want to spend the next few years answering questions and calls about why has my regression analysis crashed. But anyway, here you can see on this particular Forties example, I've kind of forced the regression here, and I've picked an arbitrary free water level at this depth, and I've forced the regression through there. And you'll note, or you will possibly note, that I've got some quite high residual oil saturations down below what I've adopted as a free water level here. And I know that in the past BP they used to adopt quite a horrendous sigmoidal function, which I don't think was on my first list or whatever. It's a very complicated function that tries to match this lower high residual oil saturation below this free water level, and then come up here and also match the oil saturations in the main leg. For the purposes of this piece of work, I just was doing a quick analysis, and I just forced the free water level through here and fitted the majority of data in the oil leg. But if you remember this little bit of residual oil saturation there, later on in the presentation I'll show you some log overlays, and you'll see the impact of that on some of the later fitting. But anyway, the point I was trying to emphasize here, that the Tamir function is quite a nice looking function in that it has this varying degree of curvature, where it tends to happen that the lambda function is either long and lazy, all the curves are long and lazy, or all the curves have a similar curvature and they're all quite tight and sharp. So now let's introduce the Excel regression spreadsheet. This first sheet is the regression sheet. This is the one that you'll see when you open up the spreadsheet, and it's split into a number of areas in a handy color-coded sort of a way. Here is the data area where you cut and paste your log data or your core data into this area. This is the equation area where you'll do a number of the analysis equations that are copied from here down to the base of the data. This is the solver area. So here are the regression coefficients and the fitting criteria that we use the Excel solver add-in to minimize when we do the regression analysis. And here are some handy guidance notes which basically go through what I'm about to tell you, so they'll act as a useful aid memoir as well. So if you forget anything, you can just refer to these guidance notes and they go through it in a step-by-step manner. Now, because I'm passing on this Excel spreadsheet for you to use, you probably need to be aware of a couple of other things. As I said before, we'll go into a little bit more detail than you would normally do for a standard presentation, but if this is a tool that you're going to use, you should be aware that there is a tab at the back of the spreadsheet called the annotation sheet, and this is where we gather together all of the information from a number of places in the workbook and put them together here in these yellow boxes. Generally, yellow boxes are where users can input data safely, but in this particular case, this is all updated automatically. And what we see is that we get data picked up from various places in the workbook, and it's written to this annotation sheet. So the results of the regression analysis, the equations, the fitting criteria, some titles, they're all written to this annotation sheet, and then those are used and then written out to the charts, and maybe some posters if you've got posters linked with Excel spreadsheets. So the idea is that a lot of the annotation of this stuff is all automated, and so we try and avoid getting into customized spreadsheet graphing and single build chart labels. So it's all done automatically from the annotation sheet. Okay. So how do we use this beast then? So first of all, we paste our log data in, or it could be core data. We have a well here, some zonation names, a depth, porosity, oil saturations, TVD subsets, or I think the new one actually is height above free water level, not TVD subsets. If you're coping with a different number of wells with varying free water levels, it's often easier to convert them all into height above free water level first, and then some other discriminators that you might use, permeability or V-shale or something like that you might want to use in your later discrimination. So you've pasted the data in here, and then you copy the equations down from the first line to the base of the data, and then you sort the data on TVD, SS, or height above free water level. So everything is now in depth order, and then you go away and you have a look at the first chart, and here is a chart already set up that will show you what your saturation with height or depth looks like. And you can see that there's not that much data in this particular example, but nevertheless you've got some log saturation here, so as we go up higher into the oil column, the oil saturation increases. So this is the top of the reservoir and this is the bottom of the reservoir, and somewhere there's a free water level. So in fact, let's pick that somewhere. We'll arbitrarily pull that. You may of course know this from other data. You may want to impose your free water level from RFTs or any other source of information you have. You maybe a known free water level, and then you also identify what I'm calling, in inverted commas, the transition zone. So in broad terms, within the transition zone here, this is the stuff between the free water level and the point at which you might expect the saturation to become irreducible. The thing that controls the saturation here is gravity, both gravity and capillary pressure effects. Well above the transition zone, above any gravity effects, the control on oil saturation should be dominated by capillary forces, i.e. rock quality. So up here, above the transition zone, the reason that this is good oil saturation is most likely because it's good rock quality, and the reason that this is poor saturation is because it's likely to be poorer rock quality. Once you're in the transition zone, you can't necessarily make that one-for-one statement, because obviously what also is controlling it here is the gravity effects, how much capillary pressure you've got to overcome. So there's a gravity term in here as well. This could be good rock, but it doesn't quite have as high a saturation as up here because the gravity hasn't generated enough force to get it in there. So generally what I try and do is I split out the transition zone. Now, sensu stricto, this may not be the capillary pressure derived, the core capillary pressure derived transition zone, and we'll discuss this a little bit later. But actually what I'm trying to do is just trying to exclude anything that might be affected by gravity, and we're going to do a lot of analysis on the rock at the highest level where we assume that the gravity effects are minimal. So if we plot those depths, the free water level and the height above the transition zone, into our regression area on our regression sheet, and if I zoom in on that a little bit, you'll see that we put those depths in, and the spreadsheet will report back to you what Excel row those depths occur at. Okay, and that's useful because when you go to this particular spreadsheet, so this chart, which is a porosity oil saturation chart, this is sometimes called a Buckles plot, although Buckles plots strictly have logarithmic scales. I tend to prefer looking at them on linear scales. I like to see the curvature of the data a little bit more. Buckles plots revert this to a straight line. So here we have, with increasing porosity, we get increasing oil saturation. So as you might expect, when you've got good quality rock, you can get more good oil into it. So the importance of knowing where the free water level is and the transition zone is it goes, if you edit this chart, the chart is set up with two data series. You edit the data series for where the transition zone begins, and then the stuff below what I'm calling this apparent transition zone plots in yellow. So yellow points on a yellow background tend to de-emphasize those, and we'll concentrate primarily on this dark data set. Now this chart is a bit different to the first one I showed you, hence we've got some more points, but the principle is the same. We're looking at the shape of the dark blue points now, because these are the ones that are hopefully just controlled by capillary quality. And you'll see here that this yellow cloud down here, which is quite reasonable porosity but very low oil saturations, only 10 to 20% oil saturation, that must be because they were way down deep in the transition zone near the free water level, so haven't developed the saturation yet. So we're interested in how the rock behaves with porosity. As you see an increasing porosity, you get a good oil saturation. Okay, so what you can do then is to use the Excel solver, and what this cell here is the equivalent hydrocarbon column. That's porosity times oil saturation, the differences between the function and the log data, and we run the solver to minimize the error in this term, the equivalent hydrocarbon column thickness, by changing these coefficients to the equation. So this is the porosity dependency equation. We run the regression, and then after we've done that, it fits a nice curve for us here, and that curve is annotated on the annotation sheet, and that's again picked up here. So the equation that we've come up with is automatically appears on this chart. Okay, and just to show you some other examples here, this is, you can see the good oil saturation, increasing porosity. If we look at some other examples from some other fields, here you can see a little bit more a better defined curve here. This happens to be a North Sea Brent formation, and you can see that as we get poorer and poorer porosity, the saturation rapidly increases. Here are a couple of related West African fields. They're very reasonably close together, but you can see that this particular one, if you come in here at 20% porosity, you might expect to see an oil saturation of about 70 to 80% oil saturation. But if you come into this field at 20% porosity, you might expect to see only 30 to 40% oil saturation. So it's quite interesting to look at these kind of plots. I find these plots very intuitive. Now here's another West African field, I think. Yes. So here it's interesting. I've got a cloud of data coming down here, and perhaps I've got another hint of something coming through here. So that's a bit confusing. So you might anticipate that there might be a couple of facies in here. So when you look at these kind of plots, you get a feel for how well is your data behaving, and do you need to partition it up? Is there something else going on? Is there one facies coming through here, and is this genuinely something else going on in the data? Now clearly most of the time you're trying to work with data in its virgin conditions before production. Any sweep has been introduced, so this is hopefully under capillary pressure control. If I just go back to a Forties example, here's that Forties data set I was showing you earlier on. Here there's obviously not a lot constraining the lower porosity end, and that's good. That's many degrees of freedom. But actually what I'll show you later is actually I've probably been a little bit too optimistic here on this particular plot. There's not a lot controlling that, but when I show you some data later on, you'll see that I'm probably overestimating the saturations. If I have 15 pu rock, in reality I don't get 75% oil saturation, but we'll see a bit about that later. And you'll see the impact of those sorts of decisions. But anyway, nevertheless, it's quite a useful thing to look at your reservoir in these terms, above any gravity effects, concentrated on what rock quality is controlling your saturation. Again, it's done in terms of porosity, because that's the most readily measured term and it's readily mapped. So if you think in terms of porosity as your proxy for rock quality, then that's obviously often the simplest thing to do. However, as we'll see later, using porosity as our proxy for rock quality as opposed to permeability can get us into a little bit of difficulty, and I'll show you some examples later on where really we should really attempt to use permeability. Permeability is subject to its own errors, of course, in the mapping of it, the derivation of it. When you're using it in 3D models, you could be introducing more noise into your result. So I try and get a porosity term to work generally, but if I have to go down the permeability route, then you have to go down the permeability route. The other thing for completeness, I guess, is we can have a look at the saturation height relationship just in terms of height without the porosity term in it. So here's a set of log data, and you can see there's quite a long, lazy apparent transition zone in these log observations. Here saturation increasing with height, but in quite a long, lazy way. So if we were going to go and do a regression analysis on this, we go back to our regression sheet, and here is the height dependency equation. Again, we minimize the errors in hydrocarbon thickness between the function and the log. We take the difference and we try and minimize this difference by reducing or changing these coefficients in the equation, and then the resultant curve we get, this is the equation of this line here, is given here again from the annotation sheet automatically, and you'll see that this is just a function of height above the free water level. There's no porosity term in there. You'll find when you do this for yourself that oftentimes the effect of these points over here tends to drag this line out of what you might draw by hand. If you were going to draw a line through this data by hand, your eye would be drawn by the centroid of this data point, and so sometimes you have to I won't say cheat, but optimize the regression to make you get a nice curve through here that you'd intuitively draw by eye. Whereas mathematically speaking, the errors in some of these terms here may be large enough to start swinging you back away from where you'd naturally draw the line. So that's the height only regression. So if you take that same data set, just with the height data, what's interesting to have a look at is the influence of rock quality or porosity. Now this graph is already set up. The chart ranges are set up. All you have to do is a little bit of manipulation on the porosity sheet. So to go from the raw data, saturation versus height, into porosity bin data, colored by porosity class, what you have to do is you have to go to the second sheet in the Excel spreadsheet, and you take your input data here from the first sheet and you paste it in here into the second sheet. And then what you have to do is you sort this by porosity. So you've copied the data from the first sheet to the second sheet, and then you've done an Excel data sort on increasing porosity. And then you basically take these equations and you copy this equation down here for each TVD SS, or height above free water level, for each of this porosity class. So here from 10 to 13 PU, which is these few points here, you copy this height here, and then you take the next one. So from 13 to 16 PU, you copy that height there, and you continue doing that, and you copy the equation down just in these chart ranges, because the chart has already been set up to pick up this as the y-axis. Now this is where Jan and I sort of diverged a long time ago. Jan's latest spreadsheets, or his later spreadsheet, sort of did this automatically, ran a macro and did all of this binning for you automatically. And I always enjoyed, strange person that I am, I always enjoyed doing this manually, communing with the data. I felt it was quite therapeutic to cut and paste these equations down, looking here where your porosity class is changed. In a way, it sort of removed some of the black boxy feel about it, because when you sort this porosity out, if you've got any negative porosities creeping in, or any porosities over 100%, then when you start cutting and pasting and copying formulas about the place, you start to get a feel for your data. So I quite enjoyed doing this manually, but I think Jan's spreadsheet is a bit more sophisticated, and he developed macros to doing that automatically. But nevertheless, the key thing is the graphs are already set up, and all you have to do is copy these TVDs or heights down for each of the porosity bins, and then you find that it will automatically color this chart for you. And here you can see that we've got some magenta data here, which is the 12 to 16 PU stuff. The green data here is 16 to 20 PU. The red stuff is the 20 to 24 PU, and here is the 24 to 28 PU in the blue. And you may or may not notice that the predominance of that good quality rock is up higher in the oil column. There's not much 28 PU rock down here, and that'll lead on to some other issues we'll discuss later on. So then you go and you do the regression, and you fit the lambda function, the porosity modified lambda function, to this data, and also the equations of these lines are all set up to take the bin average data. So the porosity of this blue line, for example, is 10.6 PU, which happens to be the average porosity of all the data that occurs in the 8 to 12 PU bin. Similarly, the magenta curve here is at 14.5 PU, which is the average porosity for all the stuff that occurs between 12 and 16 PU, and so on and so on. So as we get increasing porosity, increasing rock quality, you can see that this blue data here is the equation, the porosity that goes into the equation of this line is 0.253, which is the average porosity between 24 and 28 in this data set. Again, this is one equation sometimes people get a bit confused with this. This is just this one equation gives all these lines. All I've done is I've applied the same equation to different porosities just to give you these overlay lines to give you a feel for it. But that's one equation provides all these relationships, and again it's written out to the annotation sheet and then is reported back here on the chart. Okay, so what we've done here is this is the height and the porosity, this is the height and the porosity dependency on the regression sheet, and once again we minimize the errors in saturation, hydrocarbon volume, between the function and the log data by changing these coefficients here of the equation. There's an H0 term in there which I've had cause to use once. It's a modifier to the height term. I wanted to see if I could get an extra degree of freedom sometimes when I have an entry height effect, but most of the time this is set to 0 and I just regress and change these coefficients here, and I find that generally the lambda function is nice and stable. I press solve and it gives me a nice set of equations and fits, no problems at all. Here's a couple of examples of the crossplot QC checks that are routinely carried out. Here's two examples. There's a page of them. There's a set of crossplots here plotting the function saturation versus the versus the actual log saturation, and here is the oil volume calculated from the function versus the actual oil volume from the log data. And it's oftentimes the volume plots that you'll want to show to management because they often look nicer. So this is porosity times oil saturation, but it's primarily the thing that you're interested in, and they often show a nicer distribution than these saturations, these fractional pore volume saturation cross plots. So here's two examples, and here you can see these black lines are actually free regressions, and so they're not fixed or anything like that, and what you're looking for obviously is a nice one-to-one correlation between these plots, and what this first set here is, that's the porosity only function that we discussed at the beginning. So that's the match you get from just matching porosity above the transition zone. Here is the height only function. So here in this particular case you can see it's a little bit skewy, doesn't quite match the unity line, and here is the porosity modified saturation. So that's the final one, if you like, the match between log and saturation in a crossplot term, and so you're looking for that in oil volume terms to be around the unity line, and that looks like a pretty good fit. Here is another equation that's slightly modified, what I've called the complex height and porosity function, but that's currently not on the spreadsheet anyway. But you can see this is a set of QC crossplots that you have a look at, and they demonstrate the fit that you've got by cross-plotting the predicted versus actual, if you like, of your saturation. Now, one thing you should be aware of in Excel, and I call it a quirk of Excel, Excel doesn't seem to cope very well with nulls on charting. So the problem I find is that this data is picked up from the regression sheet, and the equations, they do some lookups, and if cells are blank, they return a blank number in the equation. So if there is no data pasted from your data pasted area, then the equations return these spaces, and then unfortunately when you come to chart them, Excel doesn't seem to like charting these blank text spaces in a series of numbers, so you have to go in and manually blank them. So here, remember, this is back on the regression sheet. This is the data that you've pasted in, and you will have remembered that you will have copied this row of equations right down to the bottom of your data sheet. Now initially you'll see that the data, these equations will automatically be blanked out because they'll be returning the text string, blank text string. But what you need to do to get those charts to work is you need to go in there, highlight this bunch of cells, right click and clear all, and then this is the data up until the top of the transition zone. You have to clear this column and clear this column. Now I do this at the end because obviously if you're playing around and changing the free water levels, then the depths at which these these automatic blanks occur, change a little bit. So get the regression right, get happy with your free water level in the transition zone, and then once you've finished, you've got to remember, well, you'll go to the QC plots and you'll find that they don't plot out right, and then you'll remember, come back to this Excel, to the regression sheet, and manually blank out everything below the free water level. And then for these two columns of data, you'll have to manually blank out that porosity relationship as well, so that your QC cross plots will work. I'm sorry that's a little bit clunky, but I haven't found a way to get Excel to plot or ignore blank numbers when it's trying to do an XY cross plot. Okay, so the other thing you should do as well, if you've got the nerve, is to plot your functions in log data space. It's all very well looking at cross plots and determining regression coefficients and thinking you've done a good job. Oftentimes the proof of the pudding is when you overlay your equations on your original log saturation. So here I've got an example from the North Sea, a North Sea field, a Brent field, and some saturations from a West African field. And if I overlay the resultant saturation height functions on there, you can see that in general I've got a pretty good match. So I think this is a lambda function. Yeah, these are the two lambda functions that I've derived for these two fields. Perhaps I'm overcalling oil saturation in that sand a little bit. See, I've got a reasonable handle on porosity. This is the hydrocarbon saturation in red, and the black is the function fitted to it. Not doing a too bad a job. Here in West Africa, we've got a similar thing going on. Perhaps I'm slightly overcooling in some of the poorer rock quality. Now if I go back and have a look at that Forties example I was showing you earlier on, here's some Forties wells. Here's the function this time is in red, so that's the lambda function that I calculated compared to the Archie saturation in blue, and you can see that I'm doing a pretty good job in the majority of the sands, but when the rock gets poorer, I'm tending to overestimate. And you remember when I showed you that porosity plot, you could see that I had quite a number of degrees of freedom, so I would probably make that a little bit harsher. As this porosity decreases, I would probably change that if I was doing it now, just to get a little bit better match in this poorer rock quality. Of course you have to be a bit careful, because some of that may be shoulder bed effects of these shales nearby, and so how much of it is due to the suppression of the resistivity by the surrounding shales, and how much of it is genuinely a rock quality effect. But I think I've got a couple of degrees of freedom. I could probably get a little bit better match in this porous zone. And here you see, here's where I impose that free water level, comes in here and matches this stuff here, and this little blob of stuff down here is that residual oil saturation. We see it here as well, that residual oil saturation below what I've selected as a free water level. Now I don't really know the full field history here, I haven't really worked Forties before myself, but you can see that if you did have a nice sigmoidal function, you might be tempted to try and get something to fit through there as well. But I kind of suspect there's a history of hydrodynamic behavior in the Forties system, and maybe there are some relict oil below free oil levels, or paleo oil contacts or whatever, that have moved up a little bit, and maybe this is no longer in the same capillary pressure regime anyway as this main oil column. Here you can see I'm doing a pretty reasonable job, considering that all the porosity is 27%. It's not doing too bad a job. Okay, so let's go back to the main presentation now. One of the other things we can do is we have a look at the porosity distribution in our data set. How representative is our porosity? So one of the charts on here is going to plot the cumulative porosity from the log data that we've pasted in. Here is the blue log data that we cut and paste in, and underneath it you can just about see that's a best fit normal distribution. So I've used the Excel function to put a normal distribution on there, and you can see from the overlay that this particular data set is very normally distributed. So you might draw some comfort from that if you believe that sort of thing, that this is a normal set of porosity with a normal distribution, so it's fairly representative. Just to show you that I don't fiddle them all, here are some other examples from some other fields I've worked on. Here again the blue data doesn't quite match the pure normal distribution shape, so you could say it's not actually normally distributed. Here in this particular example you could see a slight bimodal distribution here, as we've got a bunch of rock at 17 pu and then another higher proportion of rock at 22 pu, so that's almost like a bimodal distribution. Doesn't fit on the normal distribution. And here again, by looking at these sorts of cross plots, you're getting a feel for your data and getting a feel for how reliable your analysis is going to be if you've got representative data. Okay, so there may be some other trends. Let's get on to discussing some other complications. And this is where I get onto things like diagenesis and stuff like that. Here, there's a cross plot in there that automatically plots out the porosity depth relationships of your pasted data. And here you can have a look at this data, and as you can see that as we go deeper in the structure, we lose porosity. It's quite a typical effect, and sometimes this can act to enhance the apparent transition zone. So what do I mean by that? Well, if we have a look at this particular data set, or if you have this data set has quite clearly a decreasing porosity with depth trend, and that can actually enhance the apparent transition zone. So here are all those data sets. Now if we just concentrate on the 24 to 28 PU bin, so these are all the same porosity bin from that data set, and you can see that apparently we have a sort of a 600-foot transition zone. And typically, reservoir engineers don't like that kind of thing. So our porosity depth trend, remember, overall we had the best porosity at the top and the poorest porosity down below. That can act to sort of stretch out the apparent data. When we look at it just in saturation terms, it gives us the appearance of a saturation transition zone. And particularly if we put some capillary pressure data over the top of this is core cap pressure data from this field in the same porosity range, 24 to 28 PU, and you can see that the cap pressure data has a bit steeper, less pronounced transition zone. So again, that seems to be indicating that the log data is giving us a longer apparent transition zone. But if we consider perhaps what's going on is in this field there is a bit of diagenesis going on. We see that permeability for any given porosity may change with depth as well. And so up here, this is all 24 to 28 PU rock, but perhaps, and now I don't know this for sure, it's a while since I've worked on this data set and I don't have the permeability data to hand, but perhaps this 24 to 28 PU data set has a higher permeability, 250 millidarcies say, and perhaps this 24 to 28 PU has only 150 millidarcies, and this one maybe 75 millidarcies. So in permeability terms, if we were able to predict permeability and map permeability reliably, then perhaps we would have less transition zone because we'd have a set of cap curves that match these permeability trends. But when we're working with porosity and height in log saturation terms, you can see that although we think this is all the same rock quality because it's the same porosity, you can see that the data is smeared out and actually enhances, if you like, this apparent transition zone. But sensu stricto, it's not really a transition zone, it's potentially just an artifact of the permeability distribution within our porosity bin. I hope I explained that reasonably well. Here's another example where actually a reverse porosity depth trend may act against our transition zone effect. So here at the top of this reservoir we've actually got lower porosities, and as we go down in the reservoir we've got some higher porosities. And what that can do when you look at the saturation versus height plot, if you ignore this data down here at the free water level, you can see we've almost got an upside down free water level trend. We've got high water saturations here and increasing oil saturations down towards the base. So that's, if you just looked at that data, it would be a bit confusing. I think it's an upside down transition zone, but if we look at the porosity plot of this data, the Buckles plot, it's quite interesting that you've got quite a well-defined control on saturation here. In fact, you've got quite a clear trend here, good set of data there indicating that the saturation is increasing here, and that's quite well constrained. And in fact, you can obviously see another cloud of data coming through here indicating we've probably got another couple of fascies here. So there is a strong control of porosity on saturation, and if we color this data up by porosity, again, it enhances it. We can see quite clearly that this rock up here from 6 to 10 PU is very poor, hence the poor oil saturation. Here we've got 10 to 14 PU, and as we get increasing porosity, we get increasing oil saturation, and that comes out quite clearly because in this particular case the porosity control and saturation is very strong. And if we run our analysis, black box it, and we just run a regression, there you go. That's what Bill Gates says is the minimal reduction, minimal error between the two predicted and actual measured saturations. Now, of course, not many geoscientists were going to like that, like the look of it. Mathematically, it may be the best prediction of the average saturation for use in the 3D model. Perhaps if you are just doing a model for 3D volumetric purposes, perhaps that is the minimal error that you would get if you put that equation into your model. However, most people would like to see something that look a little bit more geological. So here, what I've done is I've just forced it by putting a little data point up here, and I say I condition the regression to satisfy these criteria. Okay, so that appears just here on the spreadsheet, just off-piste to the right-hand side of the regression sheet. The user can put in some height functions here, and you can pick the minimum and the maximum porosities, and then it will calculate what saturation you would expect at 600 feet above the oil water contact with the 26% porosity, and then you can add that as a condition in your analysis. So when you do the analysis to fit this function, you can do it with a constraint that this has to be less than 95%, for example. So I said at 600 feet above the transition zone, above the free water level, force this point to be less than 95%, and then you can run the analysis that way, and it gives you a more reasonable looking set of curves. Now, arguably here would be a good use of the Tamir function, because here you can see everything is quite all the curves are fairly parallel, and it says that every bit of rock quality, it gives you quite a sharp transition zone, whereas perhaps you might want to draw a more lazy transition zone up through this poorer rock quality stuff and gradually get a sharper and sharper curvature until you get to this plot. Furthermore, you could probably play around with the free water level. Arguably, there might be a shallower free water level here that you could fit through this cloud. But again, you have other offset information for picking that free water level, and those are the sorts of games that you can play around with. I guess I'm just trying to show you the tools that you can use to sometimes force a more intuitive answer. So anyway, finally, in conclusion, these functions are certainly ideal for volumetric use. If you want to know what the average oil saturation is in your reservoir and apply it in a 3D model, I think for volumetrics these functions are absolutely fine. They can also be used for reservoir simulation. You can convert the height term to a capillary pressure term and use them for simulation, but for reasons that I've hinted at there with the permeability term, they're not necessarily exactly the same as the core capillary derived curves that are most used for setting up in the simulation world. Using the porosity, obviously it's readily mapped, readily available, and we don't have to rely on permeability mapping assumptions. Again, we can introduce more error by our estimates in permeability, or not being able to map permeability appropriately. But nevertheless, there are some times where you do need to consider the permeability effects and maybe derive a function using permeability equations. Okay, so I also find that saturation height functions are an excellent log analysis check. So I always do a saturation height modeling exercise on most of the petrophysical work I do, whether anybody asks me for a saturation height function or not, because I find that if you just measure Archie in a log analysis sort of a way, you're missing some of the understanding that you get by attempting to fit saturation height functions to your log analysis data. It does give you an idea, a further insight into the way that your reservoir is plumbed together, and are you getting the right Archie saturation for the saturation height that you expect. So if you have that preconceived idea, then you can spot errors and issues arising with your reservoir when things don't match up, and oftentimes you learn more from where the saturation height functions don't fit than where they do. There are other functions that we've discussed, the porosity modified lambda, because it's robust and applicable to both log and cap pressure data. You can put core cap pressure data in here and carry out the same types of fitting techniques as we've used here. I briefly mentioned the Tamiya function because that's another favourite of mine, but it's a little bit more of a trickier regression implementation. And the final point I've sort of mentioned as we've gone through this is I'm fitting by minimising the errors in equivalent hydrocarbon pore volume. I'm not just minimising the errors in the saturation difference. I want to minimise the errors in predicted hydrocarbon pore volume. After all, that's primarily what we're most interested in, hydrocarbon or oil volume, and minimising the errors in water saturation is of less interest. So all of this work is predicated on fitting to equivalent hydrocarbon pore volume, oil times porosity. Okay, so that's all I had. Thank you very much for your attention.